Okay, we're on to chapter 11. So with that, so we're going to hop back and talk about the some of the basic reactions, stuff like that. So after our foray into structural analysis, and so what we're going to be talking about primarily are the reactions with alkyl halides, stuff like that. But really, the big thing that we're talking about is the substitution and elimination reactions, stuff like that. So with substitution reactions, right? So you get, obviously, as the name implies, you get a substitution effect. So you're going to have the nucleophile here, which is the it's nucleophile, for it's nuclear for positively charged and phile for loving, right? So it's going to be liking positive charge, right? So when you have something like this, a compound like this, right? So the bromine, right, being the more electronegative, it's going to have a partial negative charge, partial positive charge. So wherever your nucleophile is here, so let's say it's hydroxide, right? Those electrons, right, are going to be attracted to the partial positive of this carbon, right? Attack there, right? So carbon, because it has the two hydrogens, right? So it has its 4 bonds. It doesn't need another one, so it's got to push one away. It's going to push away the more electron, the weakest bond, which is right here. To get to result in the OH coming in and substituting, replacing the bromide here. But now the other thing that can happen is that instead this hydroxide, instead of reacting at that carbon, it can actually rip off that the hydrogen, so it's going to act like a base instead. And so those electrons collapse down to make a double bond, and in doing so, kick off your leaving group here. So, but that most times it can be a halide, but there's other things that can be here. So you have your with substitution, you have your nucleophile acting like actually doing nucleophilic attack, or you have the nucleophile acting like a base where it rips off a hydrogen and collapses down and leaves the double bond scar. So you have this sort of duality of your nucleophile. We'll talk about what makes good for what. Okay, so one of the things for the discovery of these things, one of the things that was noticed was that in general, right, you have your X would be your leaving group. Usually it's something electronegative, so it's like a halide. You had your nucleophile, and it substitutes in for the wherever that leaving group is to leave your leaving group with negative charge. One of the quirky things about it is that with nucleophilic reactions, one of the things that can happen is you can actually invert the stereochemistry. And so this OTOS, which is a tosylate, which is its sole purpose in life is to leave. Right. So what can happen is if your leaving group here is on a wedge, when you attack here, it'll actually push the tosylate away, and in doing so, because of the angle of attack for doing this, because the tosylate is too big and bulky, right? So these guys come in, push in, have to come in from behind, and so what ends up happening is you actually invert your stereochemistry. This hydrogen gets pushed forward, it pops forward, and your leaving group leaves. It doesn't matter if the tosylate's in the front, if your leaving group's in the back. So in this case, there's a bromine, on a dash. The cyanide nucleophile comes in from the front, which would be the backside of your where your nucleophile is. The opposite way it's pointing, it comes in and attaches on this wedge, right? Pushes the hydrogen over and pops off the bromine. So either way, you're going to get an inversion of stereochemistry. So with these kinds of reactions. Okay, so with that, and so there's a couple of different types. The first one would be what are called SN2. And stuff like that. So here it's what we sort of normal classic substitution reactions with that. And so you have your nucleophile coming in and attacking this, some sort of carbon with the leaving group to get the substitution reaction. Now for this one, the rate of reaction is some rate constant times the concentration of that and that, right? So with that, and so since there's two things involved in the slow step. So this is the slow step of the reaction. It's considered bimolecular, which is where you get the two. So it's a substitution reaction, right? You're substituting in. It's nucleophilic, right? So because you have a nucleophile coming in and doing the substitution, and then it's bimolecular, right? Because this is the slow step. Two things coming together is the slow step, and so there's two things involved in the rate equation. So SN2 That's typically how we write these things. Okay. Now the mechanism for this, and so you can sort of see the sort of hydrogens for this one. What ends up happening is the hydrogens are inverted this way as the nucleophile comes in, and the sort of backside attack for this, right? So what ends up happening is these guys get pushed. So the nucleophile comes in here, and because it's big, it's sort of starting to push these guys away, and in doing so, it helps. That steerix ends up helping to push that bromine away and stuff like that. And in doing so, you sort of go this, and then you pop this off, and then the hydrogens pop away onto the other side, and so you end up inverting the stereochemistry. The best visual everybody talks about is that if you have an umbrella in a windy day, right? So the umbrella ends up popping like that. That's exactly what happens with the groups here. Like that. So the hydrogens are able to, or the nucleophiles come into attack here because the hydrogens are small, but they do have to get out of the way, and so they end up popping and electronically and sterically ends up pushing the electrons, or pushing the bromine away, your leaving group, to invert the stereochemistry here. Okay, so what makes a good SN2 reaction? So we're going to be going through this, the sort of characteristics of these different types of reactions. So because we're having to attack here at this site, right? So here, we need as little bulk around here as possible, right? Because we need to get the nucleophile in to be able to attack and push this away. So we need as little bulk around here as possible. So if you have even just a methyl group is fantastic, or if it's just primary, so primaries and just methyl, those are great. That's exactly how you're going to want to do it. Secondary, it sometimes works, right? Depending on how big these things are. If they get the side chains get really, really big, even if this is secondary, or even though this is primary, if the things get really, really big, it's just too bulky to push the nucleophile to push these things out of the way, so it goes slowly. If you have a tertiary, a leaving group on a tertiary carbon, it's not going to happen. Okay, so the smaller the group, the faster this goes, right? So this is going to want to go on a on a primary carbon. That's the best way to do it. Now, one side note is if you ever have your leaving group on a double bond, right? So bromine here, right? Even if it's that's still considered a primary carbon, right? This is just not going to happen. Whatever your nucleophile is, that's just not going to happen. The sterics are bad for this. It can't get quite the right angle at this, stuff like that. So this is not going to happen. Same thing with if it's on a benzene ring, right? So this is very similar to this. In order for this nucleophile to come in, right, it had to be like right in the middle of that ring and pushed here and push that away. This is just not going to happen. So if your nucleophile is directly off of a double bond, doesn't matter if it's an alkene or an alkyne, whatever, or a benzene ring, it's just not going to happen. Okay, there's other mechanisms for doing this. It's just not an SN2, and we'll talk about this a little bit later. But an SN2 reaction is just not going to happen if it's hanging off a double bond. So, okay, so the nucleophiles. So one of the things that happens is, so we're going to talk about what makes a good nucleophile. We talked about what makes the sort of the steric effects, right? So with that, the other thing we'll talk about next is the nucleophile. What makes a good nucleophile? Well, it parallels with basicity. Okay, so the stronger the base, right, the better the nucleophile in general. Stuff like that. So, for example, so OH. So if you look at the pKa table, right, so you want something as high a number of pKa's as possible, right? So with that, so because strong acids have low numbers, right? Strong bases have high pKa numbers. So hydroxide has a much higher pKa. It's like 16, right, as opposed to acetate, which is probably like 5. So with that, so the stronger, the higher the pKa, the better the base, which means the better the nucleophile. Okay, so this is in the book, and so this is a little bit quirky, stuff like that. But what they're talking about is nucleophilicity generally increases as you go down a column in the periodic table. Okay, so this doesn't make much sense if you think about what I just said, the parallels basicity, right? So by that, because what they're saying is iodine, right? Iodine, bromine, chlorine, fluorine, right? So as you go down, this one would be the strongest, right? Strongest nucleophile. and this would be the weakest, even though this is the much stronger base. Okay, the reason is that what we're talking about here is that this is in polar protic solvents. Okay, it doesn't really talk about this much, explanation as to why, but this is what's actually going on. So what happens? So a polar protic solvent. So a classic one is methanol. Okay, and so what happens is you have your fluorine, right? Your fluoride, I should say, right? It's it's very high sort of very high electronegativity. It's got a lot of negative charge associated with it. But what things that happens is, right, so if you have a hydrogen on electronegative atom, so like an OH, something like that, you're going to have a lot of you're going to have pretty significant amount of partial positive charge on this hydrogen. So it's looking for some source of negative charge or electrons, and so you're actually going to get a hydrogen bond to this fluorine here. And what ends up happening is you end up getting this solvent cage around your nucleophile. And so it's just basically trapped, right? So the best visual I can think about this is trying to run a marathon, right? So if you have a snowsuit on, right, it's going to be really difficult. It's just big and bulky, and you just can't do what you need to do to run, right? But if you have just shorts and a t-shirt on, you're probably going to be fine, right? What's actually happening is these guys here, because they're so electronegative, they're going to very much attract the solvent cage here, right? So these hydrogen bonds are going to be basically gumming up the works. So it just can't do what it really wants to do, which is be a nucleophile. Okay, the solvent cage isn't nearly as strong with an iodine as it is for a fluorine. So basically, it's almost like a steric effect, right? So you just this thing can do its business better than this one here. When you switch to a polar aprotic solvent, okay, where you don't have the solvent cage, then it follows the normal trends, okay. So an apolar solvent would be something that doesn't have this hydrogen hanging off of something electronegative. So these would be things like acetone, acetonitrile. Trying to think of another one. DMSO, which is this, dimethyl sulfoxide. Notice we don't have a hydrogen sticking off of any of these electronegative atoms, right? So these are all aprotic solvents. So these are all aprotic. I don't necessarily need you to know the structures of these things, but you need to know that the difference between a protic and an aprotic solvent and how they affect these reactions. Okay, so and so just be aware that once you switch to an aprotic solvent, it follows the regular trends. When you're in a protic solvent, right? So when you have a specific proton, where it can make these hydrogen bonds, then things get gummed up. Okay, which comes to the next slide slide in a minute. Okay, stuff like that. So again, one of the things that happens with the nucleophile, right? So things that are negatively charged, right, are going to be better nucleophiles than uncharged things. So hydroxide is going to be a lot better than just water. So even though they both have lone pairs, they can donate. They can do the attach. The fact that hydroxide has a fixed charge makes it a much better nucleophile. It also has a much higher pKa value. So that's sort of as is to be expected. Okay, the leaving group, right? So that tracks with again with basicity. Right, so the thing that falls off, the weaker the base, the more likely it is that it'll fall off. Okay, so like that. And so if you have so fluorine's it's a weak base, weak acid, right? So it has a fairly strong leaving group, so like that. So fairly strong compared to the other halides or whatever. So it's gonna be pretty. It's just not going to leave, which is why Teflon doesn't react as much. stuff like that. So, but chlorine, right, it's a pretty decent leaving group because, you know, HCl is a strong acid. Hydrobromic acid is really strong, which means bromide is very, you know, is very weak. Same with iodine. Iodic acid, again, very strong acid. So so that means its conjugate base is really poor. Stuff like that. Tossic acid, again, this would here one of the reasons why for tossic acid, right? So this is the tosylate. This is tosylate, right? So this one here, you can actually come in here. All of these atoms, except for that methyl group, can participate in a resonance structure, and so it can stabilize stabilize this negative charge. You know, here, you know, that here, you know, and you can follow that around all the different places it can go. I think it skips every one, right? So it'd be here. Or I don't know, something like that. So we'd have to draw it out, but you get massive amounts of stabilization. So it does. So when this happens, the molecule's okay. So that means it's going to leave. Okay. And so what you're trying to do is you're trying to go when you want to predict the way the reaction is going to go. You want to go from a strong base to a weak base. You want your pKa values to go down. Okay. And so this is 16. This is negative something, stuff like that. So you want to go from big number to little number. Same thing that goes here. So if this is a weak base, this is a strong base, right? So this is like 16, and this is like 30, 30 or 40, something like that. And so you're going up. And so what the reaction really wants to do is it really wants to go the reverse. So that this reaction, this forward reaction, would not go. The reverse reaction would go actually be something slightly different, but it does not want to go this way for the reaction, something like that. So the question is, so if you have one of these really poor leaving groups, right? So how do you get it to leave if you need it to leave? Well, you sort of cheat a little bit, and you sort of make it into a good leaving group, right? So you can take an OH, and we already talked about this a little bit in previous chapters. Where you take an OH, you add thionyl chloride. If you have this, right, and you want to make it into a Cl, right? SOCl2, that's its sole purpose in life is to turn OHs into Cls, right? Cls. Okay, same with this PBr3, right? So it turns OHs into bromides. Now you've turned a really terrible leaving group in an OH to a pretty decent leaving group in a chloride. Now the other thing that you can do is you can turn it into this tossic acid, tosyl chloride, COTOS. Okay, now that's ready to go for leaving. It's no different than these guys here. So like that. So this can come in and it's ready to go for nucleophilic attack. But it's an easy way of turning into an OH into something that can leave. So like that. So these are the type of reactions we're going to deal with. Okay, now one of the other ones that we talk about are these ethers are generally pretty stable, right? So like that. That's why we use them for solvents. So like that. So they don't react. The exception to this are what are called epoxides, and these are the ones, if you remember back from way back when we were talking about cycloalkanes, right? So these are cyclopropanes are pretty unstable because this guy here, this bond angle would typically want to be 109, right? And it's what, 45 or 60? I can't remember which. Anyway, there's a lot of ring strain. I think it's actually 60. Sorry. So it's really wrenched out of the normal bond angle, stuff like that. And so you're getting a lot of steric strain. And so what can happen is, right, so, but again, you have this electronegative oxygen here, right? And so you have electropositive carbons that are attached to it. So you can have whatever nucleophile you want. You can have, OH, so it's whatever nucleophile you need, right, can come in here. It's going to be attracted to these guys. Now this one is less sterically hindered than this one, right? So you can come in here and attack. And then this guy, right, it's got 1, 2, 3, 4. It's got to release one of these bonds, and so it just puts it right up there. So you end up with nucleophile, whatever your nucleophile is. And then, somewhere along the way it'll pick up a hydrogen during the workup. But notice how it's one up, one down. It's a trans addition. right? Because you're coming in from the bottom, and this pops it off, so the OH would be on the top. Say that OH would be on the top, and then your nucleophile would be on the bottom. Okay, that's all that's going on here. But one of the big things that happens, right? So you not only get the attraction here, the negative charge with this partial positive, but you also get the relief of this ring strain. And so this is a nice way of doing it. Okay, so solvents, we talked about this a little bit, right? So polar protic solvents are typically bad because they can form these solvent shells around there. And so you solvate your nucleophile and just keep it from, you basically cage it up. So about that, you can also have an issue where you have a nucleophile, right? So if you have a nucleophile, right, so it's negatively charged, right, it can act like a base. And so if you have an acidic hydrogen on there, you can react it to do what bases do, and you form this plus your OR, whatever, your OR minus, and so now you've blown your nucleophile, stuff like that. So you've just ripped it apart, stuff like that. So polar protic solvents are bad, and so what you want to do is for this you do need to have a polar solvent because you need it because you're dealing with charges. Those are going to help stabilize the charge. The problem is these things that will solvate it. So methanol and water. So you'll cage up your nucleophile and keep things going. And so what you need to do is you need to run these into polar aprotic solvents. So DMSO, DMF. This is the acetonitrile and HMPA, like that. So these generally work pretty well, like that. So okay, so that's an SN1 reaction. Okay, now we're going to talk about an SN2 or SN1 reaction. And so as the name applies, okay, so it's a substitution nucleophilic, but it's the slow step is unimolecular. There's only one thing involved in that slow step. Okay, and so like that for here, what we've noticed is actually that and we'll get to it in a minute. But it turns out that the reason why turns out for these tertiary carbons end up working out really well. Okay, primary carbons it's not going to do anything. Tertiary is going to be really good. So, because what's happening is for the mechanism is that the first thing that happens, the slow step, is going to be this guy going away. Okay, and so CH3. This thing falling apart, okay, to leave you with a carbocation plus Br minus, okay? And so if you have a carbocation here, the best way to stabilize this is with the tertiary, either with some sort of resonance structure or to be on a tertiary carbon, okay? Primary carbocations are incredibly unstable. Tertiary carbocations not too bad, right? So if this is the first thing that happens, right, because it's an SN1. Only one molecule is involved in this, okay? One molecule. It's just this, falling apart for here. Then you can come in here, right? So whatever your nucleophile is, right? That can come in and then attack, and so you'll have your then you'll have whatever your nucleophile is. Okay, so it's always this mechanism is going to be it's going to fall apart and then come here. But what happens is because this thing, these charges are planar. So let's say this was R. Okay, this was an R stereochemistry. Right. So what happens is this becomes flat. Okay, it comes in here because these sp2 hybridized carbons, right? They end up forming planar. So this is flat. So whatever stereochemistry you had here goes away. Okay, and so here what you end up having, when it comes in here, you're going to have a mixture of R plus S. Okay, if it's an SN2 reaction, if you had R, you could just get the S. But when you have an SN1 mechanism, what happens is you get a mixture of the two. Okay, so that's just what's saying here, right? Because this first step happens and it blows up the stereochemistry. The nucleophile can come in one way, it can come in the other. It doesn't matter, so you're going to get a mixture of R and S. So that's one way you can tell between an SN1 or SN2 reactions. SN2 reactions invert their stereochemistry, and for SN1 reactions, you get both stereo centers out, chiral centers out, both the R and the S. And so that gets scrambled. So the substrate, right? So what you want to do, right? You want to be able to stabilize this carbocation. The better you can stabilize that carbocation, the better we're going to be. Okay, and so small things hanging off your primary carbocations really terrible. Okay, tertiary carbocations are great. Benzylic, where you can put that charge into the double bond, or into the or allylic, where you can put it into that double bond. That works really, really well. Stuff like that. And so the tertiary, you want a lot of stuff around this to stabilize it. Okay. So the leaving group, it's going to be the same thing we're going to have with the same trends as the with SN2. You want to be able to, the better the leaving group, right? So the weaker the base that's coming off of here, the better, right? So at that. So plus if you can make water, that's a great thing to do. But iodine, it just follows the normal trends. Okay. The nucleophile, it does not matter. Okay, it doesn't matter what the nucleophile is, because that's not the rate limiting step. The rate limiting step is this right here. Right, so so whatever the nucleophile is, it doesn't matter, because that's not what's slowing things down. This is the slow step. Okay, so everything after that is fast. Okay, so if you remember back from the reaction diagrams, right? So we said this was the slow and that's the fast, right? So this is the slow step, right? This is it. Everything else after it does not matter. Everything before it doesn't matter. Everything after it doesn't matter. It's just the slow step. Okay, nucleophile isn't involved in it, so it doesn't matter. It doesn't matter what it is. They're all going to react the same. For the solvent, it's really, really complicated. Okay, it typically works. You need a polar solvent, but it gets to be complicated. Okay, there's a lot of different issues, because you need it to stabilize the carbocation, but you need to also not the shell. And so for a lot of these things, you really need to. There's a lot of solvent screening that you need to do and stuff like that. And so, stuff like that. So water, why is water, in this particular reaction, why is 100,000-fold higher than ethanol? I don't know. Stuff like that. So just know that for these things, we need just some sort of polar solvent, and away we go. Stuff like that. So now, there is SN1 reactions, right? So in biology, there's also SN2. You don't need to know this, but one of the classic SN1 reactions is actually the formation of these long chains, unsaturated veins like geranol, stuff like that. These sorts of things where the phosphate groups, these are basically just like these diphosphates. One of the ways these things work are just basically good leaving groups that help drive a reaction, right? So the diphosphate falls away, and then another, you get a nucleophilic attack from another isopentyl diphosphate. So you extend out the chain, and then it goes in and you go from there. But the fact that these diphosphates leave would make it an SN1 reaction. So like that. So SN2 reactions also help too, right? So if S-N-acetylmethionine, so SAM, right? So this methionine right here, that is a leaving group, right? So its whole purpose is to leave. Okay, so if you have right, so it's actually this whole thing, right? So this whole thing is a leaving group, and all it really cares about is that methyl group, right? So it'd be like methyl bromide, right? So the S-adenosylmethionine part, that is the leaving group. I should say S-adenosyl homocysteine, right? Without that methyl group, that is the leaving group. It's no different than a bromide. It's a biological bromide. Okay, so for elimination reactions, right? So we're going to have a couple of different types here, right? So for this one, right, we're going to be making a double bond. Okay? And so what you need to do is you're going to say we're going to be following Zaitsev rules. Okay, and so what Zaitsev noticed was that the more substituted alkene will be the major product. Another way of saying is where you have the fewer the hydrogens you have hanging off the carbon, the better. Okay, so for here, so if you're going to compare the products for this, right? So you have a double bond, right? So CH3, H, CH3, right? So which one's going to be better, right, as opposed to CH3, CH2. Notice this one has, right, this one has 3 hydrogens hanging off of it, directly off of that double bond. This one has 2 hydrogens, and so this one is going to be the major product. That's going to be the major product. Okay, so with that, I'm not, now, you know that it's 80-20, who cares? It's hard to tell. But you do know that this one's going to be predicted to be the major product. If you have here, right, so this only has 1 hydrogen hanging off of it as opposed to this one that has 2, so this is going to be the major product. Okay, so that's usually the way. It's just count up the hydrogens that are directly on that double bond. Yeah, right. So these guys don't matter. The ones, the methyl groups don't matter. It's the ones that are hanging directly off of this double bond. Okay, so a couple of different types. One is the E1, right? So just like the SN1, right? So for the ones, there's only 1 molecule involved. You're splitting these things up, right? So it's 1 molecule falling apart. Okay, so the leaving group leaves, right, to leave the carbocation. Now, what you're going to need, right? So for here, right? Oops, bromine. Right, so this guy leaves. To leave this, it's just one. It's just a single bond. To leave that, then your nucleophile comes in, and your base comes in, grabs that one, that collapses down to form this. And then these electrons here form that second bond there. Okay, so with that. So, but then in this case, this is the slow step. Okay, it's one reaction falling, one molecule falling apart. Now, the other option would be if there's 2 molecules involved, right? Bimolecular, right? So in this case, the slow step is, right, your base coming in and working here, there, there, and so. So here, the base, it's the base and your molecule coming together. That's the slow step. That's the first step. Okay? And so the product is basically the same. Oops. Okay? Plus your H base plus Br minus. Okay? But in this case, right, it's 2 molecules coming together. That's the slow step. Okay? Now there's another one where there's an E1CB. Okay, and this one we'll talk a little bit more. This one is a very, very special case of a where you have, so for E1CB, to notice this, what you're going to end up having is you're going to have a C double bond O right next to it. And so what will end up happening is it's a very special case where it's an E1, right? So this is the first step. Okay, but notice that we can get this, we can get a resonance structure here. Like that, and so because there's a C double bond O right next to where the leaving group is, you get this extra one. So this is an E1CB reaction, right? So this is an E1, this is an E2. This is an E1CB reaction. Okay, it's kind of an odd duck.
How are you?
Okay. So with that, so how do you know? So draw the major products of the reaction, right? So it's going to be really hard to tell between an E1 and E2 reaction if I'm going to ask you what the products are. Okay, and so but you are going to be able to tell if it's an E1CB. Okay, and so here we go. So here's the reaction, right? So draw the products of the reaction. Okay. So here we go. So sodium hydroxide, right? So this is the base. Okay, and so this is a CH3, right? This is an H, right? So you're going to have a hydrogen next to where the leaving group is, right? In order to be able to do this base, right? So here we go. So it can either come this way or it could come that way. Okay, and so here we go. So if it rips off this, right, the double bond is going to be there. right? So with that, and so this one, right? So there's a hydrogen there, right? So there would be hydrogen here, right? So there would be, right? So carbon, carbon on this side, carbon, hydrogen, right? So there's one hydrogen on this side for that molecule, right? If we're gonna rip off one of these hydrogens, the double bond would go there, and so now the double bond would go there, so hydrogen, and so this one here, we rip off one of these hydrogens, so there's two hydrogens left, right? So now there's three hydrogens on the double bond, right? You want the fewer number of hydrogens on there, so this is going to be our major product. Okay? So for here, right, so Cl, right? So there's a hydrogen here, right? There's hydrogens there, right? There's a hydrogen there, right? So you look on the adjacent carbons, right? Here and here and here, right? So that means there's three different products, right? So if we go, say, here, right? So it would be CH3 with a double bond there. Okay, so this one has one, two. So that there's only one hydrogen on this one, right? One hydrogen. Okay. Now, if we go on to, if we say rip off this hydrogen there, so it would end up being right there, and so there's actually two hydrogens on there, right, on this double bond, right? So there's two hydrogens. Now the other option would be to go here, to rip off this hydrogen, which ends up putting it there, which ends up being right. So here there's carbon, 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 carbon. So here there's no hydrogens on a double bond, right? And so this ends up being right. So there's no hydrogens on this hydrogen on this double bond here. So this is going to be the major product. Okay, major product because there's no hydrogens on there. Okay. Now again, for the E1CB, one thing you need to notice with these, okay, with the E2 reaction, okay, is that you need to have a hydrogen that's sort of 180 degrees from your leaving group, okay? And so the classic way to write this is to, right, so if you have a bromine here, right, something like that, and so if you have your base here, right, this has to attack here, right, so these electrons fall here and this goes away, or this comes away, and so you're left with that, plus your H base, plus Br minus, okay? If there isn't going to be a hydrogen 180 degrees from here, right, so this isn't going to happen, okay? So for something like this, where you can get free rotation, it's not a big deal, but it becomes an issue with this, you know, if you're saying on a, right, so if you have something like this, right, you have your bromine here, if there's a CH3 group here, right, so this would be 180 degrees, this would be, you know, these would be 180 degrees, right, so there wouldn't be a hydrogen here, so you'd have to pick this one. You'd have to go here. You couldn't go here because this one here is 180 degrees from that bromine. Okay, deuterium isotope effects, I wouldn't worry too much about this, only that it's easier to pluck off a, the CH bond is actually weaker than C-deuterium bonds, so that's going to get plucked off preferentially, but I wouldn't worry too much about that. Molecular geometry, right, so we're talking about this, we need to be antiplane. You know, so if you're going to look down that bond there, or if you're going to look down this bond first, right, so we're going to do that Newman projection, so this one is this here, right, so bromine's down here, hydrogen, hydrogen. This is the one that ends up getting taken, and then this one leaves. Okay, so for this here, right? If there's an issue where say that's a C, if it was a situation like this where now it's a methyl group 180 degrees from the bromine, this isn't going to happen. this has to be a bromine like that. Okay, that's where this comes into play. I was a little bit ahead of myself. Sorry about that. But notice how for here, if we can get this guy, right? So this has to be an ax. So your leaving group has to be axial, right? So it's going down. Okay. Right. So but what needs to be over here on either side has to be 180 degrees away. You know, it sort of has to be a hydrogen here. So in this case, there's not a hydrogen, right? It's a methyl group. Okay. And so, but here, if you were to look down here, there would be if you look down that bond here, there would be a hydrogen in play. Okay. And so, what can happen, right? So with that, so don't forget that you can get a you can get the chair flip, or whatever, but that moves the bromine out of that moves bromine equatorial, which means it doesn't happen. Okay, so with that, so here we go. So let's go through this example here. So here we go. So let's say, so if you have a Cl, right, HH, right, in order for this to happen, right, you need to put that up, put that there. You need to do a chair flip. Right, so that means this side goes up, this side goes down. And whatever, this is equatorial, right, because that's axial. Right? So now this becomes equatorial. This becomes axial. Now these hydrogens here, right? So that ends up being this one here, which is axial. That ends up getting reacted by the base. Collapse down, chlorine there. Right? Right? So you end up getting a double bond between there. Okay. Now, one of the things you have to worry about, right, is if you do this, okay, and if you are blocked, okay, so with that, in this case here, so even if it's right, so if you have, say, this one, right, that reaction can go. That, no problem. Get a double bond in between. Yep, get a double bond in between here, right? But so it's like, I should say, like that. But if instead, let's say this is down, this is axial, right? 180 degrees from this chlorine is this methyl group here. You're out, right? This reaction won't happen. Because this isn't in the correct orientation, so this reaction is not going to happen. Okay, so even if you chair flip it, right, this becomes equatorial, which doesn't do you any good. Okay, so like that. So be careful. So okay, now E1CB reactions. It's a little bit. We're going to talk about this, and so what can happen is. Right, so with that, so if you have choices, right, if you can make a choice, you're still going to make the, you're going to make the product, right, so with that, and so you follow that set of rules, but you can tune the reactions about whether you want an SN1 or an SN2, and so if you produce, so if you're going to, so if you have this reaction here, okay. If you do this under if you do these under E2 conditions, right? You can actually favor this pulling off this one just because it's much easier to get to this one because there's sterics involved, right? Because for E2 you have to have the base. The base is going to get involved in the small step. It's going to be a lot easier for a lot harder for the base to get access to this one as opposed to this one, just for sterics. So you can actually drive the reaction, this reaction, to go this way. Okay. Right? But if you say you want it to go here, right, you can actually wait for it to do a chair flip. Stuff like that. And so you can have this do E1 reactions where you're waiting for it to fall apart and then come in, and from there you can actually get it to go to you can get it to go on that side. Like this. And so it doesn't, so you can play with the conditions depending on what you want it to do. If you wanted to do an E1 or an E1 where you want to pick, right? So with that, if you wanted to do E2, you can, basically what they're saying is you can play with these depending on how you want to do this. Okay, now for E1CB, what's happening is the you're getting this, the base comes in, and you get this, I should have said base comes in. It's E1 because this is the slow step. Sorry about that. What's happening is you get this charge stabilization, and so whenever your leaving group is away from this, you can form this intermediate here, right? So stuff like that. And so if you have, the easiest one to see is something like this. If you have your leaving group here, so you have basically like a CH2, or you have a hydrogen here. If between your leaving group and your accessible hydrogens, you have one of these C double bond O groups, that's always going to be an E1CB reaction. Okay. Stuff like that. And so you see this here in biological stuff, for coming in here, ripping this apart, and you get stabilization. And so the primary things, okay, and so what do you need to know? And so these are the general types of trends that you need for these. Okay, so if you have primary halides, okay, these are going to be, for an SN2 you just need a good nucleophile. Okay, SN1 and E1 are not going to happen, right? Because you need tertiary carbocations to do that. So you're pretty much always going to favor either SN2 or E2 type reactions. E1CB is only if there's a good leaving group 2 carbons away from a C double bond O. Okay, that's pretty much the only way you're ever going to have that. It's a 2 away from the leaving group, 2 carbons away from the leaving group, you get a C double bond O. Okay, like that. So for secondary halides, pretty much any of these can occur, right? Stuff like that. And so it's really hard to tell if it's an SN2, an E2, SN1 or SN2. Excuse me. Yeah, I was going to say, or an E1 or an E2. You can tell pretty much if it's an S or an E, right? Depending on what the product is. But it's really hard to tell if it's an SN1 or an SN2. Or an E1 or E2. It's really hard to tell between the two. Now, tertiary is just the opposite of the SN1s, stuff like that, because you need the first step is that leaving group going away, and so you need to stabilize it. So those work pretty much in the for tertiary carbocations, stuff like that. And so they're not going to have SN1 and E2 reactions are not going to happen with primary. With tertiary halides, just because you cannot get the sterics are too poor here, stuff like that. And so here we go, right? So this is what we're looking for. If you have, right, so you can be able to say, so predict the reaction type. Okay, so it's SN1, SN2, E1, E1, E2, and E1CB. Okay, and so what's going to happen is, right, so you're going to have, right, so this first one here, it's a bromide, it's a cyanide replacing with a bromide. But it's on a primary carbocation. It's a primary. The leaving group's on a primary carbon, so it's in that substitution, right? Because you're getting substitution, and the reaction's happening on a primary carbon, so that's going to be an SN2. For here, right, it's going to be, you're getting an elimination reaction, okay, because you're making a double bond, okay. But what's happening is, since there isn't a C double bond O2 away from here, so it'd either be here or here. Oops, here or here. Right, it's either an E1 or E2, and you cannot. It's really hard to tell which one it is. So I'll actually accept either answer. For here, you're getting a substitution reaction, right? You're going to tosylate for the chloride, So you know it's either SN1 or SN2, but since the leaving group is on a tertiary carbon, right, you know that that can't happen on SN2, so it has to be an SN1. And here, what you've got is a, right, so you've got a leaving group here on a secondary carbon, so we don't know what that is, but 2 away is a C double bond O, so it's going to be elimination, right? So with that, so it's E1CB. Okay, so this is, so here you go. SN2 because it's primary, SN1 because it's tertiary, E1, E2 we can't tell. And we know it's not an E1CB, so it's really hard to tell on that one, so I'll take either answer. In this one, it's E1CB because 2 away is a C double bond O. Okay, so just an aside, so one of the things I used to do when I worked at Pfizer was there was a big push for green chemistry. And green chemistry, it really is important for a variety of reasons, right? So it can obviously prevent waste, and waste is getting more and more expensive to dispose of, right? So you have to take that into account. You can't just pour it down the drain anymore. Atom economy, right? You don't want to put in atoms that are just going to leave, right? So like that, so are there that aren't going to be. You want to minimize the amount of atoms you stick on the product, that aren't going to be part of the final your final molecule that you're putting in. You want to do less hazardous chemicals and intermediates. Not only is it cheaper to work with, handle, but it's also an issue of work exposure, stuff like that. And you have to. There's a lot of issues with making sure it's not there at the end, right? You don't want that in your final pill. Energy efficiency. Energy is always. These plants are expensive to run, right? So any little savings we can get on the plant side is good. Catalytic amounts, right? So there's just a lot less stuff you have to throw in that you have to get away from or buy, stuff like that. And then, and most importantly, worker safety, stuff like that. So you want to make sure that your workers are safe. You don't have issues with safety, with somebody getting hurt or sick. Green processes. So the question was always, what if you have a green as far as money versus green versus environmental? And it turns out that green processes, we've never come across an instance where it's more expensive to run something that's not environmentally friendly, stuff like that. So they go hand in hand. So you get something, so it works on the economic side, it works on the environmental side, and everybody's happy. And so this one here, the classic example is sildenafil, which is used for which is the active ingredient Viagra. The original medicinal chemistry synthesis was actually, they're almost always linear, so there's a lot of steps involved, because all they need to do is they need to just make the material and see if it works. And you're only doing it on small scale, so it's not a huge deal. There's not a lot of waste. But once you get into metric ton type issues, you want to make this process as short as possible. And so what you can do is you can actually pop these two parts together. So you take this part, you take that part, you put them together, but you run it in parallel and then combine it in one of the last steps and stuff like that. And so this is what you want to do for yield issues and for everything else. And what they did is this is the types of solvents that they use. And so the original process was for every kilogram of material that they made, they estimated they took 1,300 liters of solvent. Most of that was methylene chloride, which is a nasty solvent. It's a great solvent, but it's not great. It's difficult. It's expensive to work with. It's expensive to dispose of, and there's some worker safety issues. And so as this thing was scaled up, one, you eliminated the methylene chloride, and you got much cheaper and much easier solvents. And so right now, the commercial product is using, instead of 1,300 liters of solvent per kilo, now you're using 7 liters for every kilo of material that you're making. The future target's 4 liters per kilo, and most of that would be 2-butanone, ethyl acetate, a little bit of maybe toluene, a little bit of another solvent, stuff like that. So things that are very benign solvents and stuff like that. And so there's this huge push, right? So you don't have to, so this is all the stuff you have to dispose of, right? So with that, you don't do this. Solvents can be expensive, and so you get this big push to reduce solvents and stuff like that. So okay, so there you go.